So thank you, Mauricio, for the introduction. As mentioned, I'm a senior researcher at Microsoft Research in Cambridge. And although my primary involvement is on machine learning for healthcare, I will be talking about privacy-preserving machine learning today. Just a note, all of this work is a collaboration with Shruti Topal, who's also working at MSR Cambridge. And my slides are changing without me controlling them, which is quite concerning. So I'm going to now try and figure that out again. Sorry, everybody, for that. Okay. Okay, wonderful. Okay, so precursor to what we were talking about is to situate what exactly is the privacy preserving problem that we're concerned with. So, oh my God, sorry, I do not have control over my slides. Let me fix this and then reshare. It's always very ironic for someone who works at Microsoft to struggle with PowerPoint. Okay. And this goes here. I do not know how to change slide when I'm sharing on Zoom, so I'm just going to do it the old-fashioned way, I'm afraid. Okay, you're just going to have to deal with having the little thing on the left, I'm afraid. Okay, great. So the problem that we're concerned with is we imagine a hospital which is, there we go, a hospital which privately develops machine learning model on their sensitive in-house data. So this could be, for example, thinking about we're building a mortality prediction model or some other predictive system which is going to ingest private medical data as inputs. And now this hospital builds that model, and now they want to share the entire model with the world. This is not an entirely unusual thing in healthcare. People build predictive models all the time, and they then obviously want others to be able to benefit from them. So in this case, our privacy setting is to consider, okay, we have a model which includes the final weights and the architecture of the model, and we want to share it with potentially anyone who may then use it for nefarious purposes to try and learn things about the patients who had contributed their data to the model in the first place. So the challenge that we're considering is how do we do this kind of model sharing while protecting the privacy of the hospital patients? So a lot of this project is really oriented around stochastic gradient descent and differential privacy. So I'm going to kind of assume no one knows anything about these and give you a very quick overview over what I'm talking about. So stochastic gradient descent is by far the most common optimization method used in machine learning. In reality, people usually use some variants of SGD, but the basic principle is the same, although we are focusing on sort of vanilla SGD here. So the idea in SGD is to minimize some loss function by following a noisy estimate of its gradient. And this noisiness is really the key of what I'm talking about. And the way this noise comes into play is that we estimate the loss function using some sample from a batch of training examples, which will hopefully approximate the overall gradient. So now everyone is an expert on SGD. What about differential privacy? So differential privacy is a very strong notion of privacy. And the basic idea is that we can think of a database, for example, hospital's medical database, which may contain private information. We think about a query on that database, and differential privacy is a property of that query. We can say that a query is differentially private if the outcome of that query does not change much if you change one of the entries in the database. So this is the differential part of it. It's always about thinking about two neighboring versions of the data set, so they only differ perhaps in one row, and then think about how does the outcome of the query change when you change the database in this way. And this is formalized in terms of probability by basically saying that if my query is this fancy A, and I run it on my database, the probability of getting any given output should be approximately similar, even if I run it on database version 1 or 2. And the extent to which this probability is allowed to differ is given by an epsilon parameter, which is why we typically talk about epsilon differential privacy. So this epsilon sort of quantifies the level of privacy that our differentially private query has. So how do we actually make a query differentially private? Oftentimes, when we think about queries on a database, they're not probabilistic. But of course, in order for us to have the probability bounded, we need some notion of a probabilistic query. And so the way that we would do this is we take what is potentially a non-probabilistic query, so some function, it could be like compute the average income or something over my database, or compute what fraction of people have HIV. And then we can apply noise to it to make the outcome be something which has a probability distribution. And one method of doing this is called the Gaussian mechanism, where we essentially take our deterministic function and then we add noise, which is calibrated to give the desired level of privacy, which is based on the sensitivity of this function f. So for example, if you think about the average as a function, the average is susceptible to outliers. So if there were an outlier in the data set, my average could change massively whether or not that row is included, which would mean that to make that differentially private with a reasonable level of privacy, you might need to add quite a lot of noise to essentially mask the potential for the existence of an outlier. So to give a little bit more detail about this Gaussian mechanism, there's theory which basically tells us exactly how much noise we need to add to satisfy epsilon delta differential privacy. So the delta here is basically this idea that we have epsilon differential privacy with some wiggle room, which is given by delta. So delta is sort of this probability that you kind of don't have epsilon delta differential privacy. So it's usually very small. But given our desired level of epsilon and delta, we can compute the sensitivity of this function f, and then sort of plug it into an expression like this, the details of which are not important. Just remember that there is an expression, which will then give us essentially how much noise we need to add for the Gaussian mechanism to give us the desired level of privacy. Okay, so what does this have to do with machine learning? So the idea is, how do we make a training algorithm differentially private? So we think of the training algorithm itself, which is basically SGD, as the function on a database, which gives us as output some set of weights. So you do this, and then you say, okay, well, let's estimate the sensitivity of this function SGD. And if we can do this, then we use this Gaussian mechanism idea to add noise to make the whole thing differentially private. So this has been done, the citation at the bottom. And in this case, they had to restrict themselves to only convex loss functions in order to actually estimate the sensitivity here. But nonetheless, they demonstrated that you can do this. And this is the primary comparison work that I will be talking about throughout the rest of this talk. So the thing is that SGD is not a deterministic function. So when they said, okay, here's our function f, we're going to compute the sensitivity in order to use the Gaussian mechanism, they forgot that we know that SGD has randomness. So anyone who works in machine learning will know that changing the random seed can really change the outcome of your optimization quite a lot. Sometimes people abuse this and they sort of treat the random seed as a hyperparameter of their model. But in general, we know that changes to the random seed can change the outcome. And the way this manifests, or at least the way the randomness manifests in SGD, is essentially split into its impact on the model initialization, its impact on how we sample mini batches during training. So what I've shown here on the right is the two parameters in a logistic regression model. So this is a convex model with 3 different seeds. And you can see the trajectory during training. In this case, the model has been initialized identically. So all of the variability here is arising from the fact that we're sampling mini batches in different orders. And you can see that throughout training, these different seeds are going to produce different variants of the model. So the idea we have here is rather than thinking of SGD as a function on a database, which is deterministic, we think of it as essentially sampling from some distribution. So rather than giving a single set of weights, we can now have a sort of distribution over weights. And now we can ask the question, well, what is the privacy parameter epsilon of this distribution? We now have a notion of probability. We can just, compute this. The problem is we don't know what that distribution is. So in very simplified circumstances, attempts have been made. So for example, you can think of SGD as a stochastic differential equation. You can make various assumptions on the structure of that SDE, and then you can essentially get an analytic solution that tells you, okay, yes, the posterior is Gaussian, and its mean and variance look like this. The problem is the assumptions you need to make to get there do not entirely reflect reality. The problem is really that SGD itself, if you think about it, it's a sum of correlated noisy gradient steps. And that noise itself is going to depend on your underlying data and, of course, on your model architecture. So even just describing the noise in those gradients, much less how they all sum together to give you a final posterior, is ongoing work. So what we did here is we took a slightly unusual approach, perhaps, and we ran an empirical study. So whenever theory fails you, you can always run some experiments and try and learn something that way. So before I go into detail about exactly which experiments we ran, I just want to focus on what questions we were trying to answer with this empirical study. So the first question is, we have this intuition that changing the random seed is going to change our model weights, but we haven't compared to see how does that compare to what happens when we change the underlying data. So remember, differential privacy is always thinking about these neighboring data sets. So we'd like to know, is it the seed or is it the data that contributes the most to the changes in the model weights? The second question is getting at what is the intrinsic variance of this SGD posterior, which I was just speaking about. So we can try and empirically compute the sort of SGD sampling distribution, and then we can compute its variance and then relate that to its sort of intrinsic privacy. And then the third question is, okay, well, why are we doing any of this at all? And it's because we think that if we can account for this intrinsic variance, we may be able to build private machine learning models which work better because we've had to add less noise to them because there's already some noise in the process. So in order to get to these questions, we ran a grid of experiments. So in all these cases, we are thinking about binary classification. And we're considering two variations. So one is, so this is a kind of 2D grid. One is we vary the data. And in this case, I mean, we're trying to generate neighboring data sets in the sense of differential privacy. So this would be two variants of the training data where exactly one entry is differing. And the way we do this is we replace the ith element with the 0th element, which we then delete. And then otherwise, the order of the data is identical because this matters. And in the second variant, we change the random seed. And we also consider two variants there where we either fix the model initialization so that all the variability is coming from the change in sampling order, or we also allow the model initialization to depend on the random seed, which is what would normally happen in a machine learning setting. So given these two axes of variation, we also consider 4 different data sets, which are all modified to be binary classification, and we consider 2 classes of models. So the first one we look at is logistic regression, because partially pre-existing results exist here. There is some theory because it is nice and convex. And we also look at small neural networks with single hidden layer ReLU nonlinearity, which are taking us a little bit closer to what people use in practice. I will note here that these are quite low dimensional. In general, high capacity models are very difficult to make private simply because you're just releasing so many parameters into the world. So extending this to larger models is sort of ongoing work, as they say. So just to give you an idea of how many experiments we ran in the order of 10 to 20,000 experiments per data set per model class, which meant we ran, some over 100,000, trained over 100,000 models to produce these results. Luckily, these are all quite quick to train, so this wasn't like a GPT level processing job, but we did run a fair few experiments. So given this grid of results, I can now start to try and answer some of the questions we're interested in. And I realize that I'm coming up to time, but I hope they'll forgive me for my PowerPoint issues at the start and give me a few more minutes. So our first question was, is it the data or is it the seed? So I'm going to talk everyone through this plot. What we're showing here is a distribution over pairs of trained models. So this is, I train logistic regression on MNIST with dataset variant 1, and I compare it with logistic regression on MNIST with dataset variant 2 with the same seed. That would be this goldish region. So this is where the seed is the same, but the data is different. In the other two, we say the data is the same. So we're training a model on exactly the same data, but we're varying the random seed, and we're either fixing the initialization of the model, or we're allowing that to also vary with the random seed. So what we can see immediately is when we change the data, oh, and sorry, what I'm actually plotting is the L2 distance between the model weights. So this is like our notion of sensitivity when we change the data. So what we see immediately is that when we change the data but fix the seed, the difference on our model weights is really much smaller than what happens when we change the seed, which is roughly what our initial intuition was, but we really wanted to formalize this. A second point is that we have this gold vertical bar here, and what this is actually the theoretical bound on the data, on the sensitivity to dataset perturbations for convex functions like what we have in logistic regression. And what we have here is if we think about the maximum of this distribution over changes in the data, this is our empirical estimate of that sensitivity. And this demonstrates that this theoretical bound is really quite loose, which is interesting because it means this is what we use to compute how much noise we need to add in the Gaussian mechanism. So we're already ignoring anything about the randomness in SGD. The looseness of this bound is indicating that we're already adding unnecessarily much noise. And just quickly, this is the same plot for all 4 data sets for the 2 different model classes, and we see qualitatively the same result in all cases. Okay, so that's question 1. Looks like the seed is having a bigger impact. So question 2, what can we say about the sort of posterior distribution of SGD? So at this point, we make a huge simplification, which is that we assume the model weights are independently and identically distributed and they're all Gaussian, which is an assumption that people make. We would love to relax it, but for now, we're gonna live with this. I've plotted a bivariate distribution of 2 weights here. So you see they kind of look independent and they kind of look similarly distributed, but by no means are we claiming that this is true. So having done this, what we're trying to do is essentially, and this is plotting sort of the flattened distribution over all the weights. It looks kind of Gaussian. It's maybe a bit more heavy-tailed. What we see is that, or what we want to compute is something along the lines of this red line, which is the variance. So we can do this for our 4 data sets, and then we can relate it to the intrinsic privacy. So the first thing is we compute, as I mentioned, this standard deviation from the weight distribution. Also point out at this point that everything has to happen at convergence, because obviously if your model has overfit horrendously, you're not expecting to have a lot of privacy. So we can compute this standard deviation for both logistic regression across the 4 data sets and for neural networks across the 4 data sets. We can then relate it to the sensitivity, both theoretical and empirical, across both logistic regression and neural networks. For neural networks, we do not have a theoretical sensitivity because they don't have the properties that we need to have such a bound. And we can see once again that the difference between the theoretical and the empirical, where we have it, is quite large, indicating that these bounds are not tight. And then given these, we can use this Gaussian mechanism expression to try and estimate a sort of intrinsic epsilon value. So if we had to give a number to how privacy preserving SGD is sort of without adding any noise, this is what we would get. So what is a good epsilon is a little bit up for debate, but lower is better. You usually want something lower than 1. So we see the smallest that we're getting here is 1.25. Which indicates that you should not assume that SGD is privacy preserving by default. Okay, I'm almost done. The third question is around utility. So we see, okay, SGD is not intrinsically privacy preserving, but it has a little bit of noise in it. So is this going to make any difference to the private models that we produce? So we essentially compare the noiseless model, the model where you add noise assuming SGD is deterministic, and then the model where you account for the randomness in SGD, as we have done through our empirical study. And what we find is, so we see, okay, we've got our noiseless performance, it is what it is. If we use SGD as deterministic, obviously there is a fall in performance because it's a privacy preserving model. Now we've had to add noise. And if we account for the randomness, we get a very small but statistically significant improvement, which increases in size roughly with these different data sets. We do see there's obviously variability across these data sets. And what we also see is that when you use the empirical sensitivity, you get a much bigger improvement because that bound is a lot tighter. Okay, I'll wrap up now. So what does any of this mean? So in summary, I'd like to argue that we should be considering this inherent stochasticity when we're building our private models. Although the improvements we've seen are quite modest, they are consistent, and we think that with more engineering, we could probably figure out how to improve the improvements that we've observed. I've already sort of gone through these results, so I'll skip to the exciting part. Is we're very interested in collaborating on this. There's a lot of unanswered questions and more follow-up work to do. So if you are interested in this topic, please reach out to me. Some of the questions we have are, of course, around relaxing this assumption about IID Gaussian, also understanding we have these 4 different data sets, where the differences arising from, what about variance of SGD, what about engineering SGD, and then, of course, all of the very many theoretical questions about SGD. So with that, thank you very much. Sorry